Okay, so in when we are doing finite element analysis, there are a few things that you need to do. There are a few steps that you have to do. I have listed down 10 steps here, and the first step is very important, which is you really have to understand the problem lah. What exactly we are trying to get some solution to, and mainly for mechanical people, we will draw free body diagram. So when you draw free body diagram, you will still remember there are few things that you need to do. You have to apply all the necessary loads and restraints. It might be this thing is not moving in the y-axis, this one is in y and x, and then applying the load. And of course you have the body itself lah. So you have to isolate the body. Next, we must do something called a sanity check, which is to check with manual calculations or published results. Make sure our calculation is not way off. Then we need to plan the analysis lah, whether your analysis is a static analysis, whether it's dynamic. When you have time domain variant, so it is dynamic. Whether your analysis is linear or non-linear, and then whether you're supposed to approach it using 2D or 3D element lah. And you need to start with a simple geometry. So if you do a very complicated geometry, you are not going to be able to troubleshoot easier. So start with a simple geometry, simple assumptions, and then later we can improve the complexity of the modeling lah. For example, if you have like 10 loads, don't put the whole 10 loads there first. Put a few loads first, and then make sure it runs properly. Then you add more boundary condition and loadings. You need to decide what are the boundary conditions, or whether you have any constraints on your model, whether do you need any connector elements. We will learn more on what are connector elements later lah. And apply proper load on your model, whether it is a point load, whether it is a surface one. Point is like this, right? Surface, the whole surface, or whether it's the whole body load. So body load is things like gravity, centrifugal force, inertia, things like that. Surface is typically pressure. So we gotta check on our material properties also, whether your material properties is isotropic or orthotropic, whether it is constant or whether it is temperature dependent. So isotropic is the typical material that we are faced with lah. Isotropic meaning if you are looking at elastic modulus, so isotropic meaning at any different direction the elastic modulus will be the same. So E in X, E in Y, E in Z also same lah. Typically it is isotropic in any direction. However, sometimes, for example, if you look at laminates layer, maybe this one is a printed circuit board, PCB. Inside your PCB, you have all your coppers, copper tracing, wiring of the copper. So something like this, and this one, right? So maybe EX and EY is the same, tapi EZ is different lah, because of the direction. So this one is, we call it orthotropic. So you need to make sure your elements are suitable, whether you are meshing using a linear or quadratic, whether it is hex or tetrahedral. And then look at your solution, what kind of solver you are using, any time step, sub-step, or any non-linearity that you need to take care. Sometimes you can do mass scaling to improve your solution time. And afterwards, we do the post-processing lah. So there are many steps lah typically. Typically, we can categorize them into three things, which is pre-processing. This is taking a lot of time. This is the one that the engineer is doing lah. And then afterwards is processing. Processing depends on your CPU. And finally, post-processing. Post-processing is important because you make decision based on your post-processing results. Interpretation of your results. So today we're going to do this problem. So this problem, I have taken this problem from Hibbeler book. This is a simple truss structure. You have 400 Newton at the top here, and you've got 600 Newton to the right hand side here, and over here you've got a rocker joint, and over here you have a pin joint, rocker and pin, and something like this you need to convert them to a free body diagram. So you need to apply that. For example, I've got a reaction force here, this one. You have to really draw it inside your model . This one is external load, of course you're going to draw it. This one is also external load, you're going to draw it. However, this one you might miss out. This is the reaction force, and since we have a pin joint, it cannot move in the X direction, cannot, Y also cannot. So you have to draw it in two axes which is CX and CY. This is the most critical part of your analysis, which is converting the problem into a free body diagram. Afterwards, we can model. So if you solve it using, for example, you can choose method of joints. So for example, you solve this particular joint. Maybe you might still remember what are the forces involved inside. You can really solve it manually. And if you solve it manually, you're going to get an answer like this. I think you're going to get something like this. This is a theoretical answer that you will get if you solve it manually. You can look at certain joints. What are the forces acting on the joint? And you can determine also whether your members are in tension or whether your members are in compression. So these are the things that you can manually do. However, today we are going to solve it using a computer. So we're going to start by doing a little sketching on the problem. Okay, so let's start your software. And then of course you need to create file and then new, and then click on part and then click on OK. So number one, we need to draw first. Draw this beam truss structure. So you've got 6 meter and then 4 meter and then 3 meter section . So it's like a trapezium shape. So when we are drawing here, you guys can go to features . Under here there's a lot of things. For example, features, sketch. Some of the things here you might not have it. It's fine. So just go to features . Features, and then click on front plane. So if you are going to sketch on the front plane, you can right click and then hit sketch. So it will align properly with your view. So now you can take a rectangle like this and then hit escape . press escape button, click on smart dimension, and then you're going to put a value lah. So it should be 6,000 lah, since we're drawing it in millimeter. 6,000, and then put another dimension here, 4,000, like so. And then click this one, click align, and then connect this line to somewhere here. Just put a value somewhere there. And then you need to do some trimming lah. Trimming, normally you will use this one, trim entities, and then hit this button and then just clear the section lah. And then we can draw another line over here to this end, hit escape. Finally put another dimension, which is this dimension should be 3,000. So now we have a sketch that is exactly the same as this problem lah, which is 6 meter, 4 meter, and 3 meters. So once you're done, you can exit your sketch view from here, click it, and then exit your sketching view. So you're going to see a sketch like this lah. And next thing that you need to do, you need to go to weldments. So if you cannot find this weldment, you can right click on any tab. For example, features, I can right click and I can just turn on whatever I want here. I can turn on surfaces if I need to. I don't need it. I can turn it off. For example, I don't need SolidWorks MBD. I don't need it now. I can turn it off. I think it makes your loading a little bit faster if you turn it off. However, the thing that I need now is weldment lah. If you don't have it, turn it on. So weldment is the feature that you need in order to draw beams lah. So under weldment, you're going to see sketch here. So you're going to click on structural member. So this structural member, you can select ISO and then select whatever beam shape that you want lah. For example, if I want a C channel, and then I can select a dimension 120 by 12, and then I can click on the item lah. Just click on the beam, and then I can continue doing so, and then so if I want to click the fifth item, I cannot do that lah. So normally weldment is like doing welding, so you need to do welding like one closed loop lah. If I want to add another one, I can click new group, and then I can add another one. So currently I have 2 groups lah, and I hit OK. So this is your weldment lah, currently being done using C channel. So this is our beam, something like this. This is a beam. If I want to change the profile of my channel, I can just right click and then edit feature. For example, I don't want a C channel, I want a SB beam, for example. Let's try, what is it about? And then click OK. This is an SB beam or an I beam good. So looks like a beam. Obviously not suitable, so I change. For example, square tube. Square and rectangle Square is different rectangle is different. Rectangular tube lah, 120 by 80 by 8. 120 is the width, 80 is the height, 8 millimeter I think is the thickness lah. So let's check. Okay, so you're going to get something rectangular lah. So if you need to do any modification on this rectangular shape, you just go to sketch. This is a sketch 14. Right click, edit sketch. So you're going to see this profile here. This profile, I think you need to click Control 8 on your mouse, no, on your keyboard. Control 8, yeah. 120 is the height, 8 mm is the thickness, and then the width is 80 lah. For example, you want to change this one, just hit, just double click here lah, right? Double click. Currently is 80, maybe I want to change to 150. Yeah, it's going to enlarge. I want to change the thickness. 8 millimeter is not enough. Maybe I can change to 15. The radius, yeah, okay. So I can change whatever the, profile I want lah. I can just exit. You can click here, exit, or hit here lah, exit. So I can change accordingly. So it's easy for you to design, sketch, do profile, do any problems with what do you call this? Structural members lah, truss structure and all. Okay, so we are going to proceed and do our analysis. It's a little bit fast, but later on you can view the recordings. For the first time, I'm going to go slightly faster. Later on, you can, once I stop recording, you can refer back to the recording. Okay, next. Next thing you're going to do is we are going to do our analysis lah, which is right click. It's already here lah, actually. You can click this one, SolidWorks, add-ins, and then click SolidWorks simulation. SolidWorks simulation, and then yeah, this tab will come out, simulation, and now we can do our analysis lah. So what do we do now? Number one, you can go here and then hit this one, and then you can click new study, and then static will come out. There are a lot of simulation that you can do here, a lot of analysis lah. You've got thermal frequency, buckling analysis, you can even do drop test, fatigue loading, pressure vessel design. This is design study. For example, you want to change the diameter, you want to see which one is optimized, you can also do this one. Non-linear analysis, and also you can do linear dynamics analysis lah. So for today, we are going to choose static and then click on OK. So there are a couple of nodes you can see here. 1, 2, 3, 4 has been created for you lah. These are nodes. So if you look at this one, if you expand this part, you're going to see a cut list. Expand it again, you're going to see all your structural member lah. You've got tube, rectangular, I've got 5 members. Expand every single thing, 5 members lah. So if you look at here, you're going to see solid body, right? The icon here is actually beam icon lah. So this is actually beam elements. So you need to select all the components first. Why are we doing this? We are going to convert this. No, I cannot do this. I gotta do it one by one. Right click. Treat as solid. What do I do here? Right click. Details. Material is not defined. Is it this one? No. We are going to change this to truss analysis. Edit definition, I think. Click on edit definition, and then currently is considered as beam. So beams, we will do beam analysis later on, but for the time being, we are going to choose truss. So beam is slightly more complicated. You've got a lot more options available, and you've got sections. But now we're just going to choose truss. So everybody can change to truss. How do I do this? Just select the whole thing by clicking Control, right? Right click, edit definition, change it to truss. Beam is more accurate lah, but for the first time we're doing this, we're going to use truss first lah. So our part is okay. Another thing that you need to do is that you need to apply material. So you can click apply material to all bodies, or you can put some favorite material that you have already lah. So now we're going to learn to create new material. Right click, apply material to all bodies. So this table will come out, and you can minimize this one, minimize again. There are a few folders here. You can even create your own material. For example, right click. I cannot create my own material. I have to go here and then, oh, cannot, it won't allow you to do this on SolidWorks material. You have to create your own folder lah. Can I create my own library? You can create your own library and create your own category. Then you can create lah. For example, I've got some categories here already. So let's say I want to create a new one. Right click, new library. No, under here, custom material also can. New category. You can put a new category. Under this new category only, then you can put new library. Yeah, cannot. New material here. You've got this one. So click new material. Let's say this one is steel truss. So this is the material name. There are a couple of things here. Red color. So red color is important. Black color is you don't have to put it there. You can remove it. Thermal conductivity, you don't need it. Remove it. Remove all the thermal conductivity. Red color is a must. Blue color is very good to have lah. So elastic modulus, maybe you can put 210 E9 according to our practical lab lah, which is the 200 E9 no, wrong. So 200 E9. Poison ratio, it's a 0.3. Mass density is 7,800 kilogram per meter cube. Tensile strength, you don't know actually. So maybe you can put something like 300 exponent 6 lah, which is your 300 megapascal. Yield strength is slightly lower, normally maybe 240 E6. So these are the things that you can put lah for your material. You can save it, and then you can even apply it. So once you apply, your material will come out with an icon there, steel truss. So it has a material already. So we are almost at the end of our analysis already. Next, you've got your part, you've got your material. Afterwards, we need to do some fixture lah. Fixture is something like a boundary condition. It's like how do you constrain your model lah. This is regarding this part lah, how you constrain. Where A is going up, CX and CY is being held together. So let's create some fixtures. So right click here and click fix geometry. Afterwards, you need to choose the best one is this one lah. Use reference geometry. Next, we are going to click lah. So this one is the blue color box. This is your parts where you want to constrain lah. So I'm going to click this one, and then I'm going to click, actually I'm going to hold the whole structure and make sure it doesn't move in the z-axis. So meaning it's like a 2D plane lah. Later on you'll see. Okay, I'm going to select all the joints, 1, 2, 3, 4. So all 4 joints. I'm going to select a reference plane. This pink color is like a reference plane. The best reference plane is of course your front plane. So I'm telling these 4 joints do not move in the z-axis. So z-axis is normal to the plane. I'm telling this structure, please do not move in the z-axis. So the problem becomes like a 2D problem lah. I don't want it to bend to the rear side nah. So there's this function called reverse direction. It doesn't matter. It is the same lah. It doesn't move in any direction. So this is what you do when you want to make sure your problem is in 2D lah. Okay, this is done. I need to put some more lah according to this one. I have AY. AY is being constrained upwards. Again, fixture, I have one already here. Right click, fix geometry, use reference geometry. I want to hold this joint, select my reference plane, which is my front plane. I don't want it to go up, right? Up and down, constraint. So I put another arrow there. So this is I'm telling this joint do not move lah, 0 mm. So click OK. So I have constraints in this direction already. And finally, look at here. I've got CX and also CY. I need to do one more lah. Right click fixture, fix geometry. Click this one. Oh no. Choose this one. Use reference geometry. Join 14 is okay. My reference plane will be front plane. And it cannot move in the y-axis. And it should not move in the x-axis lah. Like that. You can see clearly now. All my constraints. The first one is making sure my model is in 2D. It doesn't move to the back. The second one is constrain the simply supported. And the third one is your pin joint. So we are almost done. We just need to apply some loads lah. External load. Look back at our problem. 400 Newton going down. 600 Newton to the right. So external load, click on right click on force, and then over here you've got a few options, whether it's on vertices, whether it is on joints, or whether it is on the beams. So choose joints. Where should I put? This one lah, this joint. Reference plane is always front plane. Direction, I suppose it is this way. If you need, you can click this one lah. Reverse direction, the value is 400. Like that. And then click OK. Finally, I've got another load. Right click, force. Click on my joint, another joint here. Reference plane will be your front plane. Finally, the direction is on the along direction here. The value is 600 lah. Of course, if you need to, you can choose this one, reverse direction. I think my direction is correct already, 600. And then click on OK. There you go. So these are my model's boundary condition, the green color. And then I've got my loads, which is the purple color lah. You might not be able to see these big icons. If you need to see these big icons, you have to slightly change lah. Under simulation, go to options. I change my default options. For example, my load and fixture, I change it to big 500%. Default will not be that big default. So this is where you select some options, customize your FEA. graphic user interface lah, GUI. Okay, so I'm almost done. I can just right click on the mesh and create a mesh. So now it has created a mesh for me. I cannot see it. If I want to see it, I can click details. Click mesh details over here. Right click, details. You're going to see total nodes is 4. And then total elements is 5. These are my elements. The whole thing is an element. You cannot see. The nodes are here. So this is trust structure. Trust structure is very simple. It can run very fast. And that's it. I'm done. I can just click run this analysis or run this study. And I will be able to see the result already. Click. You can click spacebar. Spacebar. And then click whatever face you want to see. Oh, like that. Okay, so these are the results. You can see some distortion there, but it's not actually there. Deform results. Right click, edit definition. You can see that the deform shape is actually enlarged 100,000 times over. If you click through scale, you cannot see anything good. I don't think so. You cannot see anything. However, in order to verify your analysis whether it is correct or not, you can verify them by looking at something called least beam forces and least result forces. This is where you verify your results. So before we verify all these results, there are a few things that you need to do, which is it's good to change the units. How do we do this? You can refer to the worksheet. How do we do this? We can right click on the stress and then click edit definition. Over here you're going to see a few things. Change this one, Newton per meter squared, changed it to MPa. And then another one here, chart option, change your scientific to general. And finally on settings, fringe option, change from continuous to discrete. So if you can see the color here, right? The color here actually it's movable. Currently it's discrete. You can see clear distinction between the gradients. If I go to continuous, I don't see any clear distinction. So easier normally to choose discrete. How do I get here? Right click here, edit definition. I can even right click on the results and look at more results forces. However, this one is looking at the stress results. So next thing that we need to do is, you can go here and then we're going to click on a few things which is list beam forces and also list result forces. So right click, list beam forces in SI unit, and then click on OK. So this thing will come out. These are the beam forces. If you take this one and look back at here, I think it should be the same. Should be the same. It should coincide with this one. Let us verify. I screenshot this one. Click on it. Now let's take a look whether it is the same or not. So you've got beam 1, it has a 450 Newton forces at one end and then negative at the other end. I think you choose the bottom one, this one. 450, it is positive, so this is the one which is in tension. And then if you look at another one, This one 250, I think it's also in tension. Yeah, 250 in tension. And this one is negative 600. This one is in compression. Which one? Top one. And then negative 750. Compression also negative. And then negative 200 also compression. So these are the results on the beam itself. However, if you want to look at the results on the nodes or the joints, you can look this one lah, least result forces. For example, I can look at reaction force. I just have to click lah. I've got reaction force here at the bottom, and I've got another reaction force here at the top car, right? And then I can click update. These are my reaction forces lah. Is it similar? Again, we got to check whether this is similar or not with our analysis results. Oh yeah, too big. Slightly smaller. See, can you compare? I've got 600 and 600. So positive lah, it's going like this. 600 Newton lah, correct? And then over here I've got negative 600, which is 600 to the left, and then I've got negative 200, so 200 to the bottom. You can even see the arrow there, the resultant force arrow. Can you see it? There, the arrow there. That is the I'm querying the reaction force. What other forces can I query? I cannot query any more forces. So my analysis is correct. So